Welcome to your briefing for the Albatross UAV test pilot. I'll walk you through each of the aircraft's dynamic properties in detail in this video. Utilizing Unity, we were able to model the aircraft's dynamics in real time for this investigation. The analysis of the wear reaction forces and the resulting moment was performed to first estimate a reasonable range of CG positions for the aircraft. For a tricycle aircraft, you normally want 10% of the total mass concentrated through the nose gear when calculating the relative loads around the CG. As a result, the front of the aircraft is given enough mass to provide enough controllability during nose gear steering without making the front of the aircraft overly heavy. A large static margin value brought on by too much weight over the nose may harm the gear and make the aircraft difficult to control. Also, too much weight could cause the aircraft to overturn, which would increase tail hits during takeoff. An appropriate range of CG was therefore found to be between 20% and 35% of the mean aerodynamic chord, by comparing the analyses finding to elementary moment estimates as displayed. It also should be noted that to preserve aerodynamic stability, by generating a nose-down restoring force against gusts, the neutral point should set aft the CG. Next, in the thrust test, a linear relationship between RPM and sea level thrust had been established. This can be seen in the plot shown here. As noticed, the maximum sea level thrust during takeoff is found out to be 28 newtons. The proper inputs from the pilot would result in the correct matching outputs by the control surfaces according to a static control response test that followed. This test revealed that the elevator, aileron, and radar controls of the aircraft needed adjustments, either from -1 to 1 or vice versa, and the port flap needed to be engaged by setting the value from 0 to 1. The aircraft longitudinal dynamic response was then evaluated. The wind speed and CG position affect the longitudinal pitching moment. As a result, the aircraft's pitching response to deflecting the elevator under a variety of wind conditions was initially examined. These charts show the impact that increased wind speed had on the aircraft's longitudinal stability. As seen, a reaction to a high deflection, the angle of attack amplitude, and the time to decay both reduced with rising wind speed. These plots verify that adjusting the elevator in a particular direction will cause the aircraft's angle of attack to react appropriately. After that, the aircraft longitudinal stability and reaction to shifting the center of gravity was evaluated. In this clip, the aircraft CG was put at 3 different locations. First, -0.1 meters, which resulted in nose-down moment. Next, the CG-Y component was put at 0 and resulted in nose-up moment. Finally, it was decided that the optimal location for the CG in the Y component is about -0.026, which resulted in no or minor change in angle of attack. These plots demonstrate how the aircraft's longitudinal dynamic response were affected by changing the CG location and the Z-axis. The aircraft response became more susceptible to elevator deflection as the CG was pushed aft, because the lower static margin caused the deflection to create a bigger reaction in angle of attack. After a control input with shifting the CG aftwise, the oscillation amplitude and time to decay of the angle of attack also increased. A right roll behavior appeared when the CG location reached 35% of the mean aerodynamic chord, resulting in extremely significant oscillation in angle of attack as depicted. Moreover, the aircraft does not respond with strong enough responses at forward CG values, i.e. in the negative Z-axis or a high static margin value, when the elevator were deflected. However, trimming is required for aft CG positions to counteract the maximum elevator deflection's sudden right rolling motion. Therefore, based on the results of the wear reaction test analysis as well as the longitudinal dynamic response analysis, it is recommended that the CG to be located anywhere between 20% and 35% of the mean aerodynamic chord. The aircraft's rolling characteristics were then modeled and evaluated using lateral dynamic response tests. These tests were conducted to determine how rising wind speed influenced the aircraft's roll rate for a fixed aileron input, and to confirm that the proper rudder input resulted in the proper corresponding angle of side slip for the aircraft. Finally, the damping and pitch and yaw were contrasted. These charts demonstrate that as wind speed increases, the aircraft's roll rate also rises. As opposed to that, this graph demonstrates that yaw damping is significantly higher than roll damping and angle of attack damping combined. The aerodynamic coefficient of the aircraft for varied CG, flap deflection, and elevator were then determined through a wind tunnel test. The lift coefficient value that could be achieved increased as expected as the flap deflection was increased. The highest lift coefficient was roughly 1.24 for a 40-degree flap deflection at an angle of attack value of 13.95, and the stall angle of attack was roughly 15 degrees. This was based on wind speed of 10 meters per second. The elevator trim for optimal performance would be between 0 to 15 degrees, as this range has the smallest magnitude of pitching moments among the positive coefficient of lift values. However, since flying with a high trim setting is inefficient, a compromise must be found. The maximum lift to drag ratio, which was around 14, was attained at a 40 degrees flap deflection. This is less than the value specified in the manufacturer's datasheet for the UAV, but this is probably because the wind tunnel was conducted at a lower wind speed. Since the center of gravity position of a value of 0.1 had the lowest magnitude of the pitching moment coefficient among all the values of the lift coefficient, it was assumed that this was the location of neutral point, as indicated by the blue trend line on the bottom right plot. A ground maneuvering and taxi test was conducted using a CG position within the advised range as previously described, to make sure that the pilot has adequate control authority when operating the aircraft from the ground during taxi. Here, it is illustrated that the minimum unstick speed of 27 meters per second is required for takeoff without flaps or control inputs. This is about 2.7 times greater than the predicted stall speed. Trimmed flight was achieved at a speed of 21 meters per second at a throttle of 25% RPM setting and elevator trim setting of negative 6.4 degrees. As shown, a trimmed flight was achieved at even a lower speed of 19 meters per second. As seen in this part of the video, the throttle was adjusted to 40% RPM, allowing for maximum trimmed flight at a speed of 46 meters per second. The aircraft's U-guide motion was next examined. An uncontrolled attribute typically comes from a long period oscillation of an aircraft at a fixed angle of attack. You can see that the U-guide period was estimated to be 15.5 seconds, with a natural frequency of 0.405 radians per second. This was carried out for a CG of around 0.04 meters. At last, we were finally able to perform a free flight over the test course with a trimmed and stable aircraft, aiming to maintain a speed of 20 meters per second at a target flight altitude of 30 meters.